Hi, this is John Min. Today we'll talk about building a high-performance AI machine learning accelerator using RISC-V CPU core with vector extensions. But first, maybe little words about who ANDES Technologies is. We are a founding member and major contributor to RISC-V International. We chair many task groups, and we contribute to many of the open source software projects. Currently, ANDES Technology has over billion chips shipping annually with our IP. And we have over 300 customers in Asia, North America, and Europe. And Andes is a 15-year CPU IP specialist company. We went public in 2017 in Taiwan. And we have our own architecture called Andes Star, version 1 to version 3. And for version 5, we made a decision to support RISC-V architecture. Many of our engineers and management have ties to Silicon Valley, to companies like AMD, DEC, Intel, MIPS, and NVIDIA, and Sun. We are a CPU specialist company. We only do CPU IPs. So let's talk about the agenda for today. First, we'll talk about different ways to do accelerate computing. And then we'll talk about custom extension, how we create custom extensions. RISC-V, and then we'll talk about RISC-V vector extension. And I'll bring it all together with ACE example using RISC-V vectors and a summary. Well, there are 4 ways to accelerate computing on a chip. First way is create a custom acceleration engine that could take the heavy-duty processing off. It's a custom, so you have lots of freedom, implementation freedom, but it does take a while to create a standalone processor, coprocessor engine. Take a step closer to microprocessor, CPU. We could create a coprocessor. It does take a little bit of time to create, but you could do decode and control. You have lots of implementation freedom, and it's designed for medium to heavy processing. Third way, it only works if you have control over the CPU architecture, microarchitecture. Is to add instructions to the CPU itself. So basically, you become part of the CPU. Everyone using the CPU can use it. So it's not proprietary at all, but it's very, very general, easy to use. Is you have the compiler as well. Last way is the user extensions. This is where you could create your own instructions, or maybe custom data path and data manipulation. So CPU handles are the control and register file and execution. You might be a little bit restricted in how you could implement it because you have to match the CPU expectations. However, it remains proprietary, and it's really designed for point solution acceleration. You have some inner loop that takes 1,000 cycles, you got to get it down to 100, or some tightly coupled, very small algorithms. So how do we define these? Well, initially it starts with software. We provide the application software to identify time-critical code on a base processor. Once the time-critical code is identified, we could create custom instructions with cycle estimation, and they're using a cycle estimate simulator. And then I could verify whether it meets my performance or not. If it meets the performance, and you move on to the right side, a hardware column, where you implement your custom function in RTL. You make sure, A, does it do what I expect? B, is it small enough, or is it the right size that I could use it? When that requirement's met, you can move on to, you're done. You could create a processor. If it's not met, you go back and start over. So what does this look like in high level in a processor? Well, think of the top line, or top graph, as my scalar CPU. So there's instruction fetch, decode, execute, memory access, and write back, classic pipeline. And custom instructions, ACE extension, actually is creating a separate data path, separate execution unit, if you will, including the decode, um, custom memory access, execution control, and your custom operations. CPU, the ANDES will take care of most of the logic and control. You only really have to worry about your instructions. So it makes it really simple to create. So once you create the instructions, what kind of acceleration can you see? And what are the side effects? Well, A, you get your job done faster. B, it has a good side effect. You save power and energy. So without custom instructions, let's say I have 1,000 instruction sequence that does fetch, decode, execute, and that takes many cycles. With a custom instruction, you might replace 1,000 operations with single instruction. So now there's a lot less fetching, a lot less decoding, and very efficient. So you save time, execute faster, you save power. It's a perfect combination. So what kind of performance do we expect? For a simple FIR filter, we expect 20 to 30 times acceleration, but then acceleration is matched with power savings. More complex algorithm like triple DES, we could accelerate it 300 times, and we can save power 300 times. So it is a very powerful tool to accelerate computing and save power. Now, instruction is not the only thing we could do. There is also custom memory ports and custom control ports for external accelerators. Nice thing about this is we could now create private buses if you're worried about data integrity, that the private buses access private memory or private accelerator. It's all available to you. So creating custom memories and controls, we have the standard ACE pipeline along with the CPU, and then we could implement custom memories. We'll take care of all the execution and control of this, but then we have custom SoC memories that the DMA capable, and you can attach a system memory as well. Many ways, very flexible in implementation. Now, let's switch gears a little bit and talk about vector extensions. Vector extensions are very scalable, designed to be very scalable and efficient at all design points, very low cost or high performance. They can be in-order, decoupled, or out-of-order microarchitectures, integer, fixed point, and floating point data types. Nice thing about all this is, no matter how it's implemented in microarchitecture, same software runs on all the algorithms, all the different implementations. What kind of computation was it targeted for? Well, computation kernels, matrix multiply, FFT, sorting algorithms, cryptography, machine learning, deep learning, AR, VR, definitely multimedia processing, networking. Imagine you could have 512-bit copies, mem copies, and scientific computing, modeling and analysis. So there's many ways to use this engine. Here's our first implementation with our world's first RISC V vector processor, NX27V. It's built on our standard 25 series pipeline, which is RV64 GCNP implementation and ANDES V5 extensions. And lastly, that's the star of the extension, RISC V vectors. It's built on our 5-stage pipeline, single issue in order processor with optional branch prediction. With the caches from 8 to 64 kilobytes, we could handle unaligned loads and stores. And if you need to, you could have a parity or ECC. Data prefetching, both I and the data cache side, is available. You could have multiple outstanding data requests. And then lastly, there are many ways to feed this engine. You could have cached, uncached loads and stores, and we could use ACE streaming port to create custom load and store engines. So here's what the pipeline looks like. NX27V. You have the integer scalar execution pipeline on top. CPU handles fetch, decode, and execution. and execution engine will send the vector instructions to vector instruction queue, and the vector processor takes over, vector extension takes over, whether it's a scalar, floating point, or vector operations. Here's the microarchitecture. We support the latest RISC V vector spec. Data types include integer 8 to 64 bits, floating point, single precision to quad precision. And then we added a couple of different specific data formats, bfloat16 and int4, which are used in AI processing. SIMD and the vector length, it's a user configurable at 128 to 56 512 bits. And three key things to note is our VPU starts execution after instructions retired. All the instructions are chainable and fully pipelined, and there are multiple functional units operating independently. So we have multiple lanes. They can operate independently if they have different features or the lengths. Lastly, we have a standard RISC V vector loads and stores, cached and uncached. And if you needed to, you could create a custom port, loads and store port, or custom memories using our ACE extensions. So what does building a custom memory or ports look like? Well, we add standard instructions extensions. We could always use system memory. Or we could add vector loads and stores or custom memory interface. And then on the right-hand side, we can build a private memory and private accelerator access. This way, if you're worried about security or your data, they can be separated from the buses. So here's an example of using a custom port to control external hardware engines. Basically, ACE or ACP has three major functions. We could prepare and send a command. CPU can do something else while the hardware engine's crunching away. And then when it's ready, we could go get results. How you declare and define all these things, you create a port command to create the port, 90 bits wide, IO type data out to send the control command to the hardware engine. You define how many ready signals you need. If you have 10 engines, they start and finish at the same time, maybe you need one. Or if they could be independent, you just need many signals. And then lastly, the data input ports. When the CPU and hardware engine is done, how much data it's going to bring into the CPU. In this example, we create 4 ports that are 256 bit wide. A lot of different ways to implement these. So for RISC V vector processor, NX27V, what kind of speedups do we really expect? Well, basic math functions, about 20 times speedup. CNN, AI CNN functions, another 20 times. And then up to 32-bit floating point matrix multiplication. We could actually accelerate this about 60 times, assuming we could feed the vector engine and it works well. So here's a floor plan of my vector processor, NX27V. You can see there are 4 lanes of 128 bits. In 7 nanometer, it comes out to about 0.2 square millimeters, including the vector engine, CPU, and the caches. So it's a very, very tight, small accelerator. So in summary, RISC V vectors open door for RISC V processors to exceed other instruction set architectures on the market. Our NX27V vector processor is the world's first vector processor. It's going to set the bar for other high-performance RISC V vector designs. And our flexible VPU configurations and options enables really wide range of applications. Very low end, use the DSP extensions. If you need to go higher, you could use vector extension to really have high-performance processor. Our ACE engine allows for massive bandwidth to feed the hungry vector engine. There's nothing worse about having a CPU or any CPU execution unit sit there empty, waiting for bubbles. Lastly, ANDES technology will continue to expand vector product families based on our VPU microarchitecture. Thank you. And if you have any questions, you may contact me at john.min@andestech.com. Thank you. See you next time.